This is RTT 2170, Radiation Physics 1. The reading that will cover this lecture is going to be from your textbook, Chapter 17, and from Huda, Chapters 4 through 6, and 13, 3A and B. I'll also have this at the end of the lecture so that you can write this down. In this video lecture, we'll talk about the principles of radiation detectors, as well as the radiation safety and shielding. For the principles of radiation detectors, this really could be classified in terms of the gas ionization type of detectors, solid state dosimeters, diode detectors, neutron detectors, and scintillation detectors. We'll start with gas ionization detectors. The three regions that you'll have to be aware of are going to be the ionization chambers, proportional counter, and the GM counter. This first section is going to be over recombination region. So this is where you have a certain voltage that doesn't have 100% efficiency. So the number of ions that are actually collected is going to be less than the ionizations created in the volume. But once you get to the ionization chamber region, this region B, this is where you're going to have a certain voltage that's going to allow for almost 100% or very close to 100% efficiency with the chamber. And your book talks a great deal about that on page 61, which is nice. This next proportional counter region is going to be this superlinear type of graph here. And then you also have the second plateau with the Geiger counter. This is going to be a region that we do not use. And there's a small region actually between here and certain curves that we're also not using. This is another way of representing the same graph where you have the recombination region here, the ion saturation or the ionization chamber region, the proportional region, that limited proportional region. So typically chambers don't necessarily operate in this region. And then you have the GM region. The reason why I have this particular graph is just to show the difference between the various energies that you could have. So although you have the same type of curve, what you're seeing is a split and you're having a higher pulse because of the higher energy associated with that beam. So now we'll focus on ionization chambers, this first region here. This is going to be a schematic of a ionization chamber where you have a collecting volume in the center here. You'll have a polarizing voltage that is set for electrodes. So this is going to be a negative electrode that's going to attract the positively charged holes. And then you'll have a positive electrode that is going to attract the electrons that are created within this volume. So these electrons and hole ion pairs are going to be created from these ionizations that are created within this collecting volume. These ion pairs will drift, go to their electrodes, and we get a charge reading that's read out. And what we know is that the ionizations that are created within the volume are going to be representative of some sort of dose. Each of these ion chambers, in some respect, will have a way to go from charge reading to dose if that's what they're intended to do. So this is a free air ionization chamber schematic, so we're going to have a very similar thing where you have your collecting volume in the center, you have your electrodes. These are to prevent spurious things from coming in and out. So these guard electrodes here, you'll have this diaphragm that kind of allows a nice perpendicular beam here, and a lead line box to prevent things from leaking out. This is actually what's used for standardizing laboratories to calibrate instruments. So if you're sending off chambers, this is going to be the type of ion chamber that you're going to put these secondary chambers that I would send out and give a calibration factor for. There's some limitations on the design when it comes to high energy beams. So there's an upper photon energy limit of 3 MeV. With that same logic, we go to a certain design for the thimble chamber. We have these within the department. This is what we use to get profiles, PDDs from our different beams, and the constructions of these are very important. So the wall material, for example, is going to be a condensed air, so it's still a solid material with an effective Z that's similar to air, but 1,000 times more dense, just so that you can actually create still a small volume chamber, and you can have a nice thin thimble wall. So the chamber wall itself must be thick enough to allow for electronic equilibrium. These different chambers are useful within the clinic. So this farmer chamber is going to give us an absolute dose reading, and that's what we basically use it for. The thimble chamber is going to be useful for PDDs, profiles, etc. The extrapolation chamber is a special type of parallel plate chamber, and that is actually useful in calculating the actual surface dose for a beam. There's also the survey type meters. So on the left-hand side for the survey meter, I call this the Ronald McDonald meter. It's actually a Fluke or Victorine. That's going to be very useful in the department, so you can use this to survey patients and make sure that they're within compliance of regulatory limits before you release them. You can also do surveys around the department to make sure that on the outside of a barrier wall that you're receiving the correct readings and that it's not too high. I would have to do this for HDR brachytherapy on the monthly QA that we would do, just to make sure that the new source that we got was, everything was still in compliance. You have something called the cutie pie. I just wanted to put this picture here. It's kind of an older picture, but still a good one. The cutie pie is used to get an MR per hour. So this one is also MR or micro R per hour. So this is reading out the Rankine specialty unit. And it all goes back to the concepts that we described previously, where you have two electrodes, a collection volume, you're collecting charge and equating that to a charge per mass. So the typical uses, this is actually adapted from your textbook. So for ionization type chambers, the thimble farmer, for example, that's going to be used to calibrate your Linacs. This is used for measuring your treatment beam characteristics. And this is actually the transmission type ionization chambers, or what's in the Linac head. This is something that we discuss when talking about the schematic of Linac, and the Monarch unit chamber is an extremely important entity. We also have the survey meters. I brought these into the OR. We have them usually around the brachytherapy suites, or around radiation storage areas. So this is going to be very useful to make sure that patients are in compliance before you release them. Now that we've talked about the ionization chambers, we'll go to the next region, which is the proportional counter. So what we do is we increase the voltage even further. We go beyond 100% efficiency, and the charge collected is going to now increase. What's happening here is that we're going to go beyond 100% efficiency because we're having these secondary ionization events. And what that actually looks like is something like this. So you have your initial ionization event, and that initial ionization event goes on to create these discrete type of avalanches where it's going to be proportional to the initial ionization. In summary, it's going to have a multiplicative effect that is the same each time. Proportional counters are very useful to discriminate the different types of radiation within a piece of contamination, for example. And it's useful for radioactive spills. The next region is going to be the GM counter. This is where you increase the voltage even higher, and now you're going to have another plateau region. But what's different here is that a single ionization event creates this avalanche, but this avalanche causes the chamber gas itself to to become in an excited state. So what you have is UV radiation that's released, it's ionizing. You'll have the entire volume of gas ionized all at once, and you get this single pulse. So this is a nice schematic taken from Wikipedia of all places, but you have the original ionization event, which is designated here. And this single event is going to cause this crazy amount of avalanches that you see here. It's very sporadic. You'll have UV, you'll have more ionizations, you have all of these different spread here, and then they'll eventually get to the anode wire, get collected. This is a comparison between a regular ionization chamber that you would see, where you have, again, 2 electrodes, you have a collection volume, incoming photon creates a certain amount of ionizations. Those ionizations get collected, you get a charge reading. And for the GM, you have an initial ionization event, you have this electron that's liberated, it's like, yes, I'm free. And then it goes on to create these crazy amount of avalanches that get read out into a single pulse. What you see on the left-hand side is that you get poor sensitivity, but a very high accuracy. So you know that the charge that's being read out is going to really tell you something about the number of ionizations that were actually within that volume. We can easily relate that to dose, for example, whereas the Geiger counter is going to have a very high sensitivity but very low accuracy. So these are not used for surveys. These are not used to calculate dose or to get the Rankine reading. These are not built for that. They tell you that something is indeed there, and that's actually very useful. So GM counters are going to have quenching gases. This helps to suppress the electric discharge caused by UV light and allows the chamber to reset quickly before the next discharge happens, which is important, otherwise the functionality would not be there. The chamber walls, instead of being air equivalent, for example, they have to be metal, a high Z material. A downside of this, you have an energy dependence, so it under responds at lower energies and then over responds at moderate energies, which you don't see in the ionization chambers. This is a schematic of what you would see with a little pancake handle here. That's what we typically call them. And the important limitation of these, based on the design, is that you have dead time. So what that means is that for a period of time, there can't be a response. So there's no pulse. That's actually no events that are recorded during that dead time. So the polarizing voltage is being reestablished. We don't get any reading whatsoever. And so this is actually really not good for high intensity radiation fields. It will well under respond in those types of fields, which is dangerous. What they're very useful for is surveying operating rooms, anytime that you have implant procedures. So we have an LDR prostate brachytherapy program. So we implant very small 4mm long seeds into the prostate with these needles. A lot of times, since they are so small and very hard to see, and a GM counter is going to be really good at making sure that you find those. I've been in charge of surveying people's feet in the OR, where I have to make sure that nobody's like walking off with a seed. I check the trash cans in the OR after the procedure and just make sure that everything is where it needs to be. I count all the seeds up. We have any of the excess that's left over, and we're ready to go. There have been times where a colleague of mine has dropped a seed in the OR, which is not fun, but you get down there and you use the GM counter with a little pancake handle and you find it, and it's fine. You wouldn't want to use a ionization chamber, a survey meter. That wouldn't be practical for that point in time. You want something to just beep and let you know that incessantly that something is there. These are good for also searching if there's any holes in a wall, if you want to look at, a Linac vault design and just tell you that, hey, something is pinging me here. So now that we've covered the gas ionization detectors, we can move on to the solid state dosimeters. So the two that I'll mention here today are going to be the TLDs, so thermoluminescent dosimeters, and the optically stimulated luminescent dosimeters. You're still going to have several questions on TLDs, even though you may not actually use these. The majority of what we're using now are OSLDs. So this ring badge is actually going to be a TLD. You want to make sure that you're reading your name off of the ring. So that way the TLD, because it's stuck right in here, that's going to be closest to the radiation source. So if you're handling radioactive material, you'll be able to get the best estimate of dose to your hands at that point in time. You'll also see these. I know everybody in here should have it. So this are going to be an OSLD. This is a typical body monitor. It evaluates your whole body dose essentially. This is a nanodot, and this is actually going to be another form of an OSLD. They're very small. They're great for assessing patient dose. So after they're calibrated towards a known standard, so after you perform a calibration in-house, so your physicist will do that, then you can use these to assess patient dose, which is great. Good for pacemakers, good for checking the dose under a bolus, or if you want to make sure that the skin's getting adequate dose, you can also put that right on the patient and then just process it and know that the plan is sound. So these are solid state materials, and what happens is when they're irradiated, the electrons that are created in those ionization events will get trapped into these what's called electron traps. So the electrons are released from the electron trap in a TLD by the application of heat. So this heat emits visible light, and that can actually be measured. That measurement can tell you something about the dose, because we can correlate the visible light that's measured to a dose. Lithium fluoride continues to be the main. It stimulates the absorption of X-rays by soft tissue. That's why it's so good. And it's independent of X-ray energy, the material itself. So again, the ring badges that we have in our department, those are going to be TLDs. So the how-to in terms of how it works is that you'll have your energy states in the crystal, which is seen here. So before the irradiation, the electrons are all happy in their little valence bands. You have the forbidden gap, sounds like the forbidden forest, but it's the forbidden gap with a trap, and then this conduction band. So what happens is you have an irradiation, so a photon comes in, it's like pew, and it irradiates the material in the valence band. The electron gets all excited, pops out, goes into the conduction band, and as it falls back down and crosses the forbidden gap, it gets trapped in one of these traps here. The only way to really read this out for a TLD is by heating it up. So once it's heated up, the electron will get out of the gap and emit. This whole process then emits light. And that light gets read out. So this is the curve that we would see in this process here. This is a whole mechanism for a TLD reader. So you have your dosimeter. Here it gets heated up. Then you have your photomultiplier tube, which is this right here. That will pick up and read the light. That signal goes in, and from there we can do the processing. So the light is proportional to the dose that you would actually correlate that to. So again, TLDs as well as OSLDs have to be calibrated against a calibrated ion chamber. So the dose response curve is generally linear up to 10 gray, which is nice because it makes our job a little bit easier. Once you create the curve, you know that you can correlate these TL units to a dose. And then after about 10 gray, it's going to be super linear. So for OSLDs, we have a very similar process where the electrons are released from the electron trap by the application of laser light. So instead of heat, now we have laser light. this visible light that's emitted is going to be measured. And the nice thing about these OSLDs is they can actually be read out several times. What they're made of is an aluminum oxide doped with carbon. Now that we've discussed gas ionization detectors and solid state dosimeters, we can move on to diode detectors. So the diode detectors that we see in our department are going to be silicon PN junction type diodes, where the P just means positive and N is negative. The P being positive represents the electron holes. The N is going to be the electrons. This is a schematic of a PN junction diode where you have a Y depletion region. You have the P and the N type here. You don't have to know how this works. I just wanted to give you the schematics just so that you can kind of see visually what this looks like. And what you would need to know from this type of diode is that it is a PN junction. So that's really the only thing to gain from this slide for your purposes. What this is well suited for is relative dosimetry, output constancy checks, and in vivo patient dose monitoring. So if you guys have done morning QA at different sites, I'm sure you've used a daily QA3 at some point. That has, that's a diode type of array, and that is really great, can be used for constancy checks. It gets calibrated annually if you can hold out for that. Some of the major limitations is that it's got a pretty strong energy dependence, a directional dependence, thermal effects, and also radiation-induced damage. So you just have to be cautious and know when to be using a diode detector. When we start talking about PDDs, profiles, we'll see that diodes are really excellent for creating or for measuring profiles, but there's some limitations with percent depth dose because there is an energy dependence. And so we'll talk more about that as the application becomes a little bit more clear. Aside from diode detectors, we also have neutron detectors. So the one that's most commonly referred to is the BF3 counter or the REM meter, which looks like this. So it's basically got this sphere. It's got a nice chamber attached to it. You just set it on the ground. It's actually a proportional counter. It's got a cadmium loaded polyethylene sphere, and it's really good at moderating neutrons. So these neutron detectors have to be built so that neutrons want to play with it, want to interact with it, which is why that cadmium loaded polyethylene sphere is important. Polyethylene is hydrogen rich and is really good at moderating neutrons. So having this REM meter is excellent for this purpose. When you're doing radiation shielding design or you're constructing a LINAC vault, for example, you would use this to evaluate the neutrons outside the door if you have a machine that's a 10 MV machine or higher. So now we can go to scintillation type of detectors. Your book, Huda, actually has a nice section on this, and I suggest reading that. So that was, I think, that chapter 13. So the schematic here is showing you that you have ionizing photons come in. You have an NAI crystal, which is typical for these types of detectors. The photons interact with the crystal. We get ionizations that are created here, light that's propagated out, hits the photocathode. This creates electrons that get cascaded down this photomultiplier tube. So essentially, we are outputting a signal that's higher than the original. So that's what the photomultiplier tube is meant to do. But really this is going to be really good at measuring activity of nuclides. It's good at discerning isotopes, measuring surface contamination, and then brachytherapy source leakage. So it's good at measuring surface contamination because of the photomultiplier tube component. So you have an initial signal that then gets amplified in the process, which is really nice. These scintillation type detectors are going to have, this is an idealized case, but they actually end up looking more like this, where you have this Compton scattering. More discrete peak here is going to be the photopeak. Now that we've covered principles of radiation detectors, we're going to go into radiation safety and shielding design. So to start, the goals of radiation safety follow the principles of ALARA, where the acronym itself stands for as low as reasonably achievable. And what we want to do is limit the exposure from man-made sources of radiation. 3 key factors for limiting exposure are time, distance, and shielding. You've probably heard this, if not once, maybe 100 times at this point, but time, distance, and shielding are your friends, and this is really important for limiting excess exposure. So before we get too far into it, we should talk about the different organizations at play here. The International Commission on Radiological Protection, ICRP. They're a group of experts interested in the safe use of all types of radiation, and they publish recommendations for protection against exposure for the international community. The National Council on Radiation Protection and Measurements, NCRP, is going to be a national group of experts who make recommendations for protection against exposure. So it's a good thing when the ICRP, NCRP, when they can agree on something. The ICRP is going to be set on the world stage, whereas the National Council on Radiation Protection and Measurements is going to be more locally involved, so within our country. Then we have the Nuclear Regulatory Commission. This is going to be a national group as well. They're going to be responsible for regulating nuclear materials on the state and federal level. Other involved entities are the Department of Transportation, so DOT. They're going to be involved whenever transport of radioactive materials is at play. Then you have the Food and Drug Administration, the FDA. They're actually the ones that are responsible for managing the linear accelerators. So linear accelerators, X-ray producing machines in general that are not nuclear in nature are going to be governed by the Food and Drug Administration. Then you have OSHA, Occupational Safety and Health Administration. So this is the group that's going to make sure that there's a safe and healthy work environment for employees. And you have, of course, the Environmental Protection Agency, the EPA, and they're going to be mainly governing and making sure that radioactive materials don't seep into the water, for example, like drinking water. Now we can move on to dose limits. So in order to account for the biological effectiveness of different types of radiation, we have what's called the dose equivalent, which is represented by H, is going to be the absorbed dose, D, times this quality factor. The dose equivalent is given by H equals D times Q, where the D is equal to the absorbed dose with a special unit of gray, where 1 gray is equal to 100 rad, rad being the old unit. Q is the quality factor, and H is going to be the dose equivalent, which is given in terms of sieverts, which is the special unit, and the old unit being rem, where 100 rem is 1 sievert. The nice thing about dose equivalent is that it encompasses the relative biological effectiveness in a broad sense. So it takes into account that different types of radiation are going to have a certain biological consequence. The recommended quality factors can be found in this table, which is taken from Kahn. You can see here that the X-rays, gamma rays, and electrons are going to have a quality factor of 1, whereas neutrons from 100 keV to 2 MeV is 20, which is relatively high, and then alpha particles are also 20. These are going to be much more biologically damaging. Since we know that dose equivalents vary as a function of tissue type and whole body exposures are rarely uniform, we need some kind of way to quantify an effective whole body dose essentially. So the effective dose equivalent is going to do a summation of each of these dose equivalents for the tissue at hand, given or multiplied by this weighting factor. This is all of the tissues that are in question. So WT is this weighting factor of the tissue, and HT is going to be that mean dose equivalent. And the total dose equivalent that's given here, HE, is going to be an effective whole body dose. This is important for when we talk about the occupational as well as the members of the public dose limits. So the recommended values of the weighting factors are going to be listed here. You don't have to memorize these types of things. I wouldn't ask you to do that. This is simply just showing you these weighting factors. Before we can go into the actual dose limits, it's important to know what we're receiving in terms of background radiation. So they're primarily from 3 sources. So we have terrestrial radiation, cosmic radiation, and radioactive elements in the body. An example of that would be potassium. So the total effective dose equivalent is 3 millisieverts per year in the United States. So what we do is we classify harmful effects of radiation in terms of 2 different schools of thought. We have the stochastic effect, which is like a probabilistic effect, and the non-stochastic effect. For stochastic effects, we see that the probability of occurrence increases with increasing absorbed dose, but the severity in affected individuals does not depend on the magnitude of the absorbed dose. In short terms, as you increase the dose, you increase the probability of the occurrence. An example of this would be cancer. So the incidence of cancer, the probability of its occurrence will increase as you increase the dose. For non-stochastic effects, it's one which increases in severity with increasing absorbed dose in affected individuals owing to damage to increasing number of cells and tissues. In short, as you increase the dose, you increase the severity. So here's a summary of recommendations. I suggest that you guys either pause this, take a screenshot, do whatever it is that you need to do. You'll need to know the occupational annual dose limits, so the effective dose equivalent limit, which is again a measure of the whole body dose. So that's going to be of stochastic effects here. So that's going to be 50 millisieverts. For extremities, for pretty much all other, except for the lens of the eye, it's going to be 500 millisieverts. And the lens of the eye is going to be 150 millisievert. And if you're trying to figure out what guidance principle to use for cumulative exposure, you multiply 10 millisievert by their age. The other one that I'm going to expect that you know is going to be the embryo fetus exposures. So if there's an occupational worker that has declared pregnancy, the total dose equivalent over the entire course of the pregnancy is going to be 5 millisieverts. The dose equivalent in a month is going to be half a millisievert. For members of the public, for continuous or frequent exposure, you're going to have 1 millisievert a year. The effective dose equivalent limit for infrequent exposure is 5 millisieverts a year. For shielding purposes, we use this 1 millisievert a year. So that's important for you guys to know. And then essentially this effective dose equivalent limit, this dose equivalent limit for lens of the eye, this is essentially our occupational dose limits divided by 10. The whole goal of shielding design is that protective barriers are designed to ensure the dose equivalent received by any individual does not exceed the applicable maximum permissible value. So what that means is that for controlled areas, which is stating that a specific area that I am protecting is going to be, if it's controlled, then that means that I am monitoring the occupational workers. So it could be the control console. It could be an area that I know that I have people with badges on, essentially. So that's going to be the 5 millisieverts a year. And again, this is going to be taken from an assumption that we might have a pregnant worker, and therefore we have to shield and anticipate that. When it comes to uncontrolled, that means people that we're not worried about monitoring, and that's going to be 1 millisievert a year, so for those frequent exposures. So essentially you just need to know that a controlled area is going to be 5 millisieverts a year, uncontrolled 1 millisievert a year. I would give you these values if you were ever asked to do a calculation on a test or anything like that. And this is taken from the NCRP report 151. So we're worried about protection. In order to know what we're protecting against, we have to understand that there are 3 different means of radiation coming from the linear accelerator. We have the primary radiation, scattered radiation, and leakage. Primary being the primary beam, so what's coming straight out of the LINAC head. Scattered meaning, maybe it's bouncing off one of the walls. And leakage just meaning that it's coming through the LINAC head. For primary radiation, we need to have a primary barrier. And for scattered and leakage radiation, we need to have a secondary barrier present. This is a schematic diagram of an MV linear accelerator bolt. A lot of them typically have a maze, which is seen here. So we have our door, our entrance, we have this maze, and we have our isocenter. So right now, the LINAC is positioned here, and then it's directing a primary beam at these 2 walls, the ceiling and the floor. So on these walls here, we're going to have a primary barrier. And on this wall, we'll have a secondary barrier. The thickness of the maze is going to depend on how close it is to the isocenter, but essentially this is a secondary wall. This equation is one that you should know just for the quiz, exam, and this is going to assist you for when you're taking your board exam as well. B is going to be the transmission factor. P is going to be the max permissible dose equivalent. D is the distance from the isocenter to whatever distance you're shielding to. And W is the workload, which is a measure of the dose per week at a meter. U is going to be the use factor, and T is going to be the occupancy factor. The use factor is going to be the fraction of the workload in which a barrier is directly irradiating, and the occupancy factor is going to be the fraction of time during which an area is occupied. Common use factors as well as occupancy factors are given here. And again, this is not something that I would expect for you to memorize at all. This is just showing you the typical use factors for either a gantry 0, 180, 90, and 270, as well as occupancy factors for adjacent walls. So if you know that you, on one side of the LINAC vault, you're going to have an office, then that means that you really have to account for that in your shielding design. B, the transmission, is going to be listed here on the y-axis. And what you do is once you have or you know what your transmission factor is, then you can see what concrete slab thickness that you need for your particular energy. These are going to be very low energy beams, whereas in this next slide we have 0.5 MeV all the way to 176 MeV, which is very well beyond what we would use. But in either way, once you figure out your transmission factor, you're able to grab your concrete slab thickness. Another way of doing this is to calculate the actual number of half value layers or 10th value layers. Usually we use 10th value layers for shielding design. So N again is the number of 10th value layers here. So you can, once you have your transmission factor, you do minus log transmission factor you get your number of 10th value layers. Then you can plug it into this equation, and you typically get the 10th value layer 1 and the equilibrium TVLs from a table. So that would be given to you as well. This is simply just showing you that this is how you can arrive at a thickness of a certain barrier. The reading again is going to be from your textbook, chapter 17, and from Huda.